Okay, so you may have to press space bar, enter, uh, and enter the password. And at this stage, you should have, if you just move these icons around on the desktop, you'll see there's a terminal, there's Firefox, there's a readme.txt file, and the slides that we were using today. So to do this hands-on session, we have made it very simple. It's self-paced. You can cut and paste from here. You should just practice with your mouse that you are able to cut and paste into the terminal window. You can always go and use the copy over here after highlighting the text and do the paste like this. But it may be easier if I, for example, just use my middle mouse button. I can just select here and paste it over here. So I hope if you can get copy paste working properly in your setup, just launch this readme.txt by double clicking here. You should have an Emacs session like this. And with this, we'll be ready to start the hands-on session. We'll go step by step with all the examples. I am monitoring the chat window, and we also have experts from our team available in case we get overloaded with questions that we cannot answer and we need to set up a breakout room. We'll be happy to do that, where they'll be able to assist you. But please let us know through the chat if you have any questions, or feel free to unmute yourself. So the first example.
Yes, Samir, where is the README file? I'm sorry.
It is this icon, readme.txt. Have you logged in to the instance?
Yes, I have.
Okay, just move the icons a little. They may have clumped together over here. Just move them around, and you will be able to just double click on this readme.txt.
Got it.
And Detlef says that don't see any icons, just the background. In that case, Detlef, just press the space bar, hit enter. You'll be prompted to enter the password. And once you enter the password, you will see a background like this with the icons. If you see just the plain background, that means you have not entered into the remote desktop yet. Is everyone else able to launch the terminal window from GNOME terminal, launch the README file like this? And actually, these are the only two things you will need besides the Firefox browser to do the entire hands-on. The first thing we'll do is just cut and paste, go to a hello numerical world. Now, this is an interesting example from the BSSW tutorial, and you can follow along by going to this URL. You can just simply copy this URL, launch Firefox, and drop it in this hand-coded heat example. So this is a hello world program to get us started with the software stack. There are many components of the software stack. We want to look at a computation of a problem. And the problem is, will my pipes freeze during a long, cold storm? Now, there is a storm expected, and the temperature inside your house is at 70 degrees Fahrenheit. And overnight lows will be at minus 40 degrees Fahrenheit. And this will last for 15.5 hours. Now, with the insulation and the thickness of the wall, the question that we are trying to find out is, will my pipes freeze? And if I look at the distance over here and the parameters, how can I find out whether the pipes will freeze? What are the heat equations that govern this? And here is a partial differential equation over here known as the heat equation. And this wall can be treated as a homogeneous material. And for now, we can just make an approximation that this pipe is very small. I will make the window a little larger and increase the font over here. I hope you are able to launch this URL in the Firefox yourself as well. And here is the equation that we will be solving. Now, in this example, we are going to discretize the numerical equation, and we'll be solving this. Here is the source directory. I want to just get a feel for the software stack. That do I have compilers that work? Can I use a tool such as Visit to plot the data? Can I compile the code and run it properly? So to do that, I'll just look at the physics of the problem. The parameters have been encoded over here. Here is the solution parameters, and you can see all the other space and time parameters here. We'll build it and run it. And to do that, please follow the instructions from the README file. I'm going to this terminal. I've done the CD. I'll do a make clean. I have deleted all the object files. And I'll say make check all. And then it's compiling the code with the -G flag. And it's running it with various options. Here is the source code. FTCS is one of the algorithms used to run this. And you can see how this update algorithm works. Now, we still don't know the answer to the question, will the pipes freeze when the temperature drops? And to do that, we'll want to plot the data that is generated from here, the temperature and the distance. And I believe the question that they posed in this is, will the pipes freeze if the distance is here is the distance, and it's about a 0.15 in the problem. And I'll use this make at the end to launch a command like this. And here is the chart that comes up. This is the 273 Kelvin at which the pipes will freeze. This line, and this is the distance in meters of how far the pipe is from the insulation. And at 0.15 meters, you can see that I am at this temperature. And the pipe is above the freezing temperature. And so the pipe will not freeze. And it's an interesting problem. You can simulate this in 3 different ways, and there are solutions provided in this directory. What I wanted to just get a sanity check is that I am able to plot the temperature versus the distance in this plot. And this is the curve that it puts out. So that if I had a very small insulation like this, 0.05, the pipe would definitely freeze. Now, what is interesting is that we made certain assumptions. The first assumption we made is that the material that we are simulating has a pipe which is very small compared to this distance. If that is not the case, and if the material was comparable in size, like in this case here, then our heat equation would not hold, and we would have to have a different numerical model. In this case, this is the thickness of the wall, and you can see that this is the pipe which is carrying the water. So please have a look at this solution. And I hope you, when you say make, I hope you also get a visit window. Visit is a visualization tool, which is plotting this map. And I hope you are able to see this. Now, is the font size over here for my text window okay? Because I'll be using this a lot. Let me just make it a little bigger here. So with this, I know I have compilers in this AWS instance. I'm able to compile the code and run this serial application. Now I will go step by step. We looked at what containers can provide for us, and we will next look at different container runtimes and go through some of those aspects as well. Here is the description of the different container runtimes that we provide. And what is a container? It is a collection of executable software that encapsulates everything, including the operating system, but it does not include a kernel. So compared to other solutions of virtualization, where you have the full VM with two separate operating systems running here with a hypervisor in between, container-based solutions have only one kernel running on the system. And so it's a lot more efficient. You can pretty much nail down your software environment with the containers and show that. Now, I want to introduce two different types of containers. The first one is Docker, and the second is Singularity. And to do that, we'll look at our image. Here. And let's look at the images that are available over here. I see there is a problem with SSH to tut 101. Actually, please do not leave. Please do not go to 101. Just use an instance numbered from 01 to 100. We have only 100 instances. There are about 40 of us, so we didn't launch more than 100. Please SSH to like a 75 or something should work. So with this, I hope you are all able to try these commands and you get the window from visit that shows you the plot. Now with this, let's go and go to the top level directory, CD to the top, and run the command docker images. Docker images will show me what images are available over here. I see an image called Ubuntu MPI. I see an Ubuntu image with 1804. And you can omit the Docker IO library. You can just use this as the name and the tag. So each image has a tag associated with it and an image ID. If you want to see what images are running, you can say Docker PS. It will show you that there is no container running right now. So I can say Docker run and then say --rm. That means after you exit from the container, please remove any artifacts from there. So every time you run this container, it runs it separately. It's in an interactive mode. The tag of this is Ubuntu:1804. And if I do a cat on etc OS release like this, I will see that it is indeed Ubuntu 1804.5 LTS. So I have a full Ubuntu system in which I'm root, and I can even mount my home directory over there. But this is just a Docker container. I just wanted to show you how you can run a Docker container with the Docker run command. I hope you are all able to use this and verify that this is a full operating system of Ubuntu 1804, which is different, by the way, from the host operating system. So if I ran the same command here, cat etc OS release, I'll see that this is Amazon Linux, because we are on AWS with Amazon Linux 2. So there are two different operating systems, one within the container and one outside. Is this okay? The next step is I'm in the home directory and I'll use the Singularity runtime. Now, a lot of HPC sites do not like Docker because of some security concerns. In fact, although it says Docker, we are actually using a more secure version, which comes from Red Hat. It's called Podman. And Podman provides the same interface as Docker. So all your Docker commands look exactly the same. But internally, we are actually substituting Docker for a secure Podman runtime. The other popular HPC container runtime is Singularity. Singularity runtime can be launched using the Singularity run command. One key difference between Singularity and Docker is that by default, Singularity preserves your user ID and permissions and mounts your home directories directly into the container, unlike Docker. So if I have an image like this, I can say Singularity run lolcow.simg. It will echo some pithy saying. I don't know what it will say, but I can run this container like this. And A is for Apple. Okay, if you run it again, it will say something else. You get the idea. So are you able to run the Singularity container, the Docker run command? We'll start from the basics of running a container, and then how do I build a container? And we'll go from there into, we'll start out very simple, build a simple container, which just writes out hello world. What is the name of the Docker alternative that has, it is called Podman, Podman. Yeah. It comes from Red Hat.
Add apples to the grocery list.
Podman. And if you say Docker, for example, all the Docker commands have help like this, Docker -- help, and then you can say Docker, say save -- help, and then it will show you this save. How do I save an image that's running? And you'll see that actually all the usage options are coming from the man pages of podman. So just substitute the podman with the Docker, but it's the same command. I hope that's okay. And now you are able to all run the Singularity container as well, right? So let's go next and see how we'll build our Singularity and Docker containers. Yes, Docker -- version shows podman 301. So I'll go to this directory, cd to the src demo containers directory. And I'm in this containers directory. Let me cat the README file that shows me how to build these containers. Okay, so the first step is that to build a Docker container yourself, you need to have a file called Docker file. Docker file is a file that you create, and you need to tell it how to build a container, a recipe. So in this case, this is the recipe. I say, please start from an image called NERSC Ubuntu MPI :1804. I'm going to add MPI program to it. And the name of the program is helloworld.c. I'm going to put it in the app directory, and then I'll say run, go to the app directory, compile it with the compiler called MPI-CC, which is there in this Ubuntu MPI base image, and then create a file called app/hello. Let's look at the hello world file over here. It's a simple MPI program. The message passing interface is what we use for inter-node communication, or even within the node. You include the MPI.h header. And in main, you initialize it using MPI init by passing the argc argv arguments from your C top level main. You can see the size of the communicator. So if I launch, say, 8 MPI ranks, then it will say size is 8. I'm just looking at the communicator called comworld, getting the size. The rank is my individual rank. So you'll have a rank going from 0 through 7. Get the host name, and then just say print statement, hello from this rank out of so many ranks on this host. Then have a barrier call where all the MPI ranks synchronize so that there is a barrier, and then there is a finalize and the program ends. So this is a simple hello world program. To use it with MPI inside the container, I just picked this from. Now it's important that when you want to do something to create the application image, you just use and daisy chain multiple commands. Each command that you do with the run creates its own layer, and it takes up room. If you run multiple commands by just daisy chaining them with the and operator, you will save space in your container, and it will be more optimized. You may want to remember that use as few run commands as you can in the recipe in the Docker file. Now you have a Docker file, you have instructions saying, please start with the base image from NERSC, like this. We also have base images from the E4S project that have support for various runtimes. You could use one of those. And then we inject this application, helloworld.c, and put it in the app directory, and then cd to that, compile it, create the binary. Let's do this. How do we do this? Well, first we execute the docker build command, and I give it a tag, a name of the container, and then a container, and then a tag. The tag could be, for example, today's date, or I could use latest. Latest is a reserved keyword, which means that it's the latest copy of that. Now, there are multiple stages. This first step was from NERSC It got that container. In fact, I have already installed this container locally, so it doesn't have to pull it in from Docker Hub. If I say Docker images, you'll see that the NERSC container for Hello World is already here. And now it has created my Hello MPI. This is the tag that I gave it, my Hello MPI, and it said it was created 15 seconds ago. So now I have a container called my Hello MPI. How do I run this? Recall our first step where we said Docker run with the --rm with the -it. I can do that and say Docker run like this. Now I have the prompt here. I'm root again, and then I can launch the MPI application, which has been built. If I want to see, I can see the /app directory, and you should have the binary for hello. You should also have MPI run in your path. And there it is. So I can just say MPI run -np4 app hello. And this is the host name. The host name is right here. And this string. So it ran the hello world application. And so I have 0 through 4 processes running. Is this okay? I hope it's running for everyone. Again, the steps are right here. CD to this containers directory, cat this Docker file, just execute Docker build command like this, Docker run, and then MPI run. And then you're still in the container. So you can say exit. And now you are exiting from the container. You are back to the tutorial login on AWS. This exit is important to continue with the rest of the tutorial. Is this okay with your first MPI Docker container? Now, I have also given instructions that if you have an account on Docker Hub and you can create one at dockerhub.com, you can push this container with your user ID by using the Docker login -u and then give your password and say Docker push hello MPI :latest. It will push this container, and if your colleague wants to download it, they'll use your full path to the container, and they'll be able to Docker pull that. So the tutorial is going to start simple, and then we'll go to a more complex application.
Thomas, what are you doing back in there?
Pardon?
I think somebody needs to be muted. It might be Benjamin Miller.
Sorry, I mute now.
I hope this is working properly for everyone. Let's try building a Singularity container next. Now we have the first Singularity container. Let's look at this simple Singularity container, where again I'm using saying bootstrap from the Docker, take the NERSC Ubuntu MPI 1804 as the base image, and then I just put a simple message in it saying run script. This is what happens when you run the container. Simple enough. So it's all this container will do is do an echo and exit from there. This is under the run script tag. And to do that, I can just say Singularity build and give it a name of the Singularity image format. And I'm giving it Ubuntu MPI.sif, and then giving it this def file. Just like we had the Docker file, Singularity being a different container runtime, they have a def file format like this. So all I'll do is Singularity build Ubuntu MPI like this.
Crux of it is that so we have a regression test suite that I don't know if you guys are familiar.
And now it will take this Docker image. It will take this NERSC Ubuntu MPI 1804, and then it will create a Singularity image file format, the .sif. But it's saying, hey, wait a minute, you already have one in your directory. It's called Ubuntu MPI.sif. Should I delete it? And I'll say, yes, please delete it. And now it says, wait a minute, you are not root. And I just see that I could have become root by saying sudo bash. So I can say sudo bash, and then it will prompt me for my password. And I say I enter the password, the same password that I used for logging in. So now I'm root on the AWS container. Now I can run this command again and say Singularity build this. It says, shall I delete the old one? I say, yes, please do. And then it builds it. Now you can see that it's
Hey.
copying the blobs.
Hey, Samir,
Yes.
quick question.
Sure.
I ran a little bit ahead, so I already got to this point, but in general, not most HPC systems, you will not be able to get root permissions, right? So
Yes.
I saw you could use minus fake root as, what's the benefit of running this as root?
So you can choose to be fake root. In fact, Podman is one of the runtimes that does not require root access to run it, to create containers. And in fact, many centers are evaluating Red Hat's Podman as a way to create it. There are certain things that you can do with a root build. And so if you had an AWS instance where you could get root like I'm doing here, it may be better to create a container like that and launch it as a normal user. So I'll exit from here after the build is completed. And now it's called Ubuntu MPI.sif. So I could run this using Singularity run and Ubuntu.sif. Oh, sorry, Singularity run. I omitted the run parameter. Now, even if you don't have root, you can also use what is known as the sandbox option and use a file system. And there are many other options that you can have to even install the container without having root privileges. I was just using root privileges to build this particular Singularity container. Does that make sense?
Yes.
Okay. So now I'll cd to the home directory, and then we'll look at running a full-featured E4S container. So let's recap. What did we learn here? We saw how we can create a Docker container. We created a simple MPI application, hello world. We ran it with Docker. We saw Singularity build, how I can create a Singularity image format. There are two extensions, the .sif for Singularity image format or .simg, but it doesn't matter. You can just say Singularity run and then run that container. And then this is the output that you expected to see, which says this is what happens when you run the container. And where was this listed? It was in the Singularity def file, where you said echo this when you run it. So you created a container, you ran it, and it echoed this simple message. So we now know how to create our own Docker container. We know how to create a Singularity container. What if I downloaded a Singularity container from, say, the E4S web page, a full-featured container that has MPI and one API and all the tools that Mike described earlier? And to do that, I'll just say, let me go to the CD and say Singularity run ecp.simg. So I have Singularity run ecp.simg, and this image is posted on the E4S.io web page. If I go to the E4S.io web page and click on the download link, I can go to Singularity x86-64 download and then download this image right here. So that's what I have done in this AWS instance. And I'm doing this Singularity run. It will load up the startup scripts, and finally I'll get a prompt like Singularity, like this. And throughout this tutorial, what we are trying to do is distinguish between what executes on the AWS instance on bare metal hardware versus what executes within the container. So Singularity is loaded the image. It has Spack, it has MPI, it has a number of these tools already in my path. And I have a Fortran example that I want to compile. So this is the famous NAS parallel benchmark. And I can just say CD to this. Now note that my home directory is already loaded. If I say, who am I? It says tutorial. It's not root. It gives you the same user as your regular user ID. And you have your home directory, and you can load other directories as well. So I have my home tutorial mounted over here, and I'll simply say make clean first, like this, and then make sweet. This will compile the LU benchmark. There is a config directory, and then there is a suite.def that describes what will be built. And I've just said, oh, build LU with the W problem size for 4 ranks. And then I can say make sweet. It picks up the compilers from the config make.def file, where the compiler name is called MPIF90, and the flags are -03 and -G. So I have the MPI with a Fortran example, and now I have built it. It has put the binary lu.w.4 in the bin directory. So now I can go to the bin directory like this and see that there is a binary over there, which I will now run on 4 CPUs, saying MPI run -np4 lu.w.4. And there it is. So if I wanted to start very simple, and I wanted an image where MPI and support for Fortran was already installed in my path, where I just had, MPI CC or MPI F90 in my path, I have that all installed through Spack in this E4S container. And I can simply just use it as an environment for building my MPI application. So before I do other things, just wanted to check if this is okay. Are you all able to run the application? lu.w.4. Now you can exit from the container. You can do other things like you can look at Spack, find, and you'll see all the packages that are pre-installed in this Singularity image. Or you don't have to even use Spack command. You can say module avail. And many of you are familiar with the module systems on the HPC sites, and you can see which modules are available. And you can see all of these Amrex, Caliper, Cabana packages that are pre-installed, and you can just say module load, and it will load those. Okay, module avail Intel. And there's the Intel compilers also that are part of this. You may have opt, Rockham, and you have Rockham installed over here. So you can see the HipCC compilers are here. And you also have support for CUDA in this by say module avail CUDA. And I have 11.3 CUDA, the latest 11.3 CUDA that's available over here in the container. So you can just load a module, compile using the NVCC compiler and so on. Now I should mention that the 100 instances that I have launched here do not have GPUs. They don't have Intel or AMD GPUs. But I have the Singularity container, which has support for all of these runtimes. Now, I have run this ecp.simg. I am in the Singularity prompt. Let me try building another application. I can either exit and again go into the same image, or I can just stay here without exiting and go to this Zoltan directory. This is a little more complicated example than the NAS parallel benchmark. So I'm in the Zoltan directory. I did not exit. I just went straight to the Zoltan from here. Is this okay? Should I just take a minute for everyone to catch up? Just cut and paste these commands, cd to the src demo npb, do a make clean, make sweet, mpi run. Can somebody just confirm? Okay, everyone's caught up. You are able to run the MPI application. Now I'm going to go one step further and then look at this. Look at this more complex C++ code which uses Trilinos. Now, earlier I just ran the MPI application, the NAS parallel benchmark, right inside the container, a single node, a single 4 MPI ranks running on a single instance of Singularity. What if I wanted to substitute the MPI? Now, on most HPC centers and maybe on your sites, you may have Intel MPI with the compilers. What if you want to use the Intel MPI to do the substitution? So first, let me build this application called Zoltan. And to do that, I have a script called clean.sh. All it does is it deletes all the binaries. So I don't have anything in this directory. Let me just remove this IP garbage files, the log files. And you can see that I have the cxx main.cpp. This is the Zoltan test case from Trilinos. Okay, here you can see that it is loading a large number of header files, including these files. and then it's doing this numerical solution to this problem. It's using packages like ePetra, Gallery, and ML. And this program requires a large number of libraries to be installed. So for example, if I looked at the compile.sh script, it loads the Trilinos module, then it does a make clean, and then it does a make. The module avail Trilinos shows me which one of these modules. There are multiple Trilinos modules over here. So I can say compile.sh. And now it's compiling the code using the C++ compiler. And then it will link in the application. So at the end, I'll have Zoltan as a binary. Can everyone confirm that they are able to reach this point? All I did is go into this inside the Singularity container. I went to the Zoltan directory. I did a clean.sh and then a compile.sh. Okay. Now, I don't want to run it with the mpage that it is compiled with. I want to run it with the Intel MPI. I want to swap the MPI in this binary. And how do I do that? Okay, so let me first show you that if I say module load Trilinos, and then I want to see which libraries are loaded in this application. I say LDD Zoltan, it will show me all of these libraries. Now you see over here, this is where the complexity of the software environment becomes clear, that we have MPI Fortran libraries, we have mumps, we have the UMF pack, we have Scala pack, we have a number of these solvers. How many of these? In fact, if I say LDD Zoltan and get a count, there are 54 shared libraries, 54 shared libraries that this application is loading. Now, all of these libraries are present in this Zoltan module, in the Trilinos libraries. And if I want to see where exactly it's coming from, say this is one of the Trilinos paths. I say ls Trilinos. Now you can see there's many libraries that are there in this Trilinos package. In fact, 207 libraries. It can take quite some time to, in fact, install Trilinos itself, because it's a big package. It has Zoltan libraries, it has tpetra, all of these libraries, which come from the container. They are there in the E4S container. Now I want to step back out of the container, and I want to launch this executable using Intel MPI. And to do that, let me exit from this, doing this exit, and be back on the prompt over here. So here, I'll go back to this Zoltan directory where my binary was just built. I can confirm that it was just built. Here's the date, and I say Zoltan. And you can see that it was built right here, 1747. We are at 1751. So before we do the substitution, are there any questions? Were you able to do the Singularity run, do the MPI NAS parallel benchmark, and do the clean and compile.sh? and we'll describe the build cache later. Here, the build cache was used to create the container that you are now using. And we have installed all the packages, including Trilinos, using in the ecp.simg container. You have done a clean and compile. Now, here is a tool called E4S container launch tool. It is which E4S-CL. All this tool does is substitute the MPI in the container with the MPI outside the container. It's a container launch tool. And if you want to substitute this MPI, either you can do it manually, which requires quite a bit of knowledge of which files you want to preload in your application, which LD library paths you want to set, because there is the Intel MPI, which is outside the container, and there is the mpitch, which is inside the container. So to use this, you can run the script, run E4SCL.sh. What this does is it sources the set vars.sh script from your Intel 1MP API installation. This is the same as module load Intel. Then it tells the E4SCL to initialize itself. It says, I'm going to use the Singularity backend. You can have multiple backends. And then this is the image that I'm interested in using. But when you launch the application, I want you to also source this file each time. It's called home tutorial source.sh. I'll do a sanity check and make sure that I'm using the Intel MPI and not the mpitch by doing a which MPI run. So this has a very simple syntax. You just say initialize, tell it 3 things, just 3 things. What kind of runtime you want to target, that is Singularity. Where is the image of your container? And then when you start up the container, are there some module files that you need to load? Something that you need to do before your application can find the libraries. In the case of Zoltan, I had to use a module load Zoltan before it could see all the libraries, right? So all that information I'll encode in this source.sh. So I could say cat source.sh. I also have to say initialize Spack by using the setup env.sh, so it knows Spack. And then I'm just saying, just load the first Trilinos solver. If there are multiple packages, you can say Spack load -- first Trilinos. And then I'm setting an LD preload for making sure that the host libraries are mounted by E4S in a certain way and loaded like that. So here with these 2 commands, I'm saying Spack load Trilinos, set up the Spack environment. This is what should happen on startup when a container is started. And then just launch the MPI run with 4 ranks on Zoltan, the same binary, but use the MPI run from Intel MPI. So this run script will invoke the E4SCL script, initialize it, and run it. It will also, I've said profile list to show me what is the current configuration of E4SCL. So here is the E4SCL. And I have a comment here from Jean-Baptiste Kutnik, the developer in our team of E4SCL. The LD preload directive is optional. It was a temporary response to bypass Spack's tamper protection mechanisms. Okay, so here, E4SCL run E4SCL.sh. So I have created the Zoltan binary using the libraries from inside the container, and now I'm swapping the MPI. Now you'll see that here is the E4SCL, it's doing the source of the set vars.sh. One API is installed, and this is the which MPI run. So I can be sure that I'm using the Intel MPI run to launch this application with the profile over here, which says this is the name of the profile. I have a backend of Singularity. This is the image. And here is what it did internally. It found 10 libraries and 9 files that it had to set up just right before that substitution could take place. But you don't have to worry about it. E4SCL does it for you. You just say E4SCL init and E4SCL launch with the MPI run. And now it's running the application. And this is the Zoltan application. It found all the libraries. It's running this. You can see the parameters. And it's running it on 4 ranks using Intel MPI. And there are various iterations. At the end, it says test passed. And then it deletes that profile that it had created in the E4SCL. So once again, all I did is ran the container, did a clean compile, came out of the container. Then I went to Zoltan and then ran this run e4scl.sh. Can I get some confirmation that this worked? I can just wait here, wait for everyone to catch up. Here is the run e4scl.sh. And there is the execution again. So to recap, what we started out with today was we looked at a very simple hello world example for numerical solvers which didn't use MPI. Then we looked at Docker and Singularity containers, how to launch them with Docker run or Singularity run, how to create Docker and Singularity containers. I had an MPI application that I created a binary for, and then I ran that. And then with Singularity, I also ran a Singularity build option. Then we went to the full-featured E4S container, which has 70 plus packages. And we compiled the Zoltan Trilinos application with that after we compiled the NAS parallel benchmark LU application. And then with Zoltan, I didn't want to run it inside the container. I wanted to use Intel MPI. So we used the E4S container launch tool to launch this. To answer Zach's question about what it does, well, E4SCL is a tool that uses the MPitch application binary interface, ABI, not API, but ABI. And it takes the MPitch ABI, which is there in the implementation of Intel MPI as well as MPitch, and it swaps the MPI at runtime. But to do that, there are many drivers, there are many libraries that need to be loaded just right in your LD library path. You need things from outside the container, like the Intel MPI installation. You need files from inside the container, the full Trilinos installation that you saw. And so using the libraries from inside the container along with the Intel MPI from outside the container, I now have the ability to create a single binary and move it from one center to another center, use the E4S container, and then just launch the binary using a different MPI. I can use the system level MPI, which is available, which may provide the MPitch ABI. There are two different hierarchies of MPI. There is the MPitch based MPIs, and there is the open MPI, which is a second flavor. We can do the MPitch ABI substitution with the MPitch compatible MPIs like MVAPitch 2 or MPitch or Intel MPI or the Cray MPitch. But one open MPI is a slightly different MPI, and we are looking in ways to do the substitution in E4S CL, and a future release of E4S CL will support PMIX based substitution. So even if you had built your application with MPitch, you could potentially use it with OpenMPI based runtime outside the container. It's a very complex process, the substitution of MPIs, and there are various intricacies that you should be cognizant of, but we try to hide all that with a simple script which just says, this is how I initialize the container launch tool, give it the startup script, this is the container, this is the runtime, and just run it with the normal MPI run, which comes from Intel MPI. So before I go further, just wanted to check if there are any questions about this.
Hi, yeah, this is Tim. Sorry about the mute incident earlier, but I do have one question about this. So
Sure.
usually, I've found that you can get some odd bugs when mixing MPI implementations, you know, compiling with one and running with another. Could you speak to if there have been any problems with that, or people have noticed any bugs creeping in because of this?
And that's a very good question. As far as I know, the ABI, as far as the implementation of the ABI, if it conforms to the MPitch ABI, there should be no problem. And many times these vendors start with their vanilla MPitch implementation and then add their secret sauce. So it already has the MPitch ABI built in, and then they can add some optimizations for their reduction operations or some better algorithms to access the memory. For example, they may have the GDR for the data transferred directly from a GPU to the network card as it goes out from an MPI send or MPI receive operations and so on. But as long as they conform to the same ABI, the substitution works flawlessly.
Okay, thank you.
By the way, were you able to run this example without any problems?
Yes, I was.
Okay, good. So we are going at a decent pace, right? Everyone is able to get enough time to try all of these examples. So I have in our schedule a full talk on Pantheon and instructions on using Pantheon, which is scheduled for tomorrow. And I'm going to skip over this Pantheon demo, which David Rogers from Los Alamos National Labs will present tomorrow. But I will go and look at the Spack, an introduction to Spack. Now, Spack is available on this AWS instance, as well as it's available in the container that I launched, the ecp.simg container. There are some commands that can help you. I just wanted to describe these and some things that can be generally useful. I hope you can see my screen properly. I'll say which Spack. And I have a comment from Zach. He says he found what he was looking for with the E4S CL profile show and list -- long, and it shares some of the code base with the tau commander tool, which you're very familiar with, which allows the the launch of the tau performance system, and so we have used some of the things from there. But getting back to Spack, I have Spack over here, and I can say Spack find to show me which packages are installed. There are all these packages. So if I want to look for a specific package, like I say, Spack find CMake. Is CMake installed? And it says, yes, I have 4 different versions of CMake. Okay. If I say CMake at 13.8.2, then it will install this. But I noticed that it has 2 different versions, 2 different installations of CMake built with perhaps different compilers over here. I can say Spack find -dl, which shows me the dependency listing of CMake. And it will show me what packages it depends on. And the hash, this hash uniquely determines a particular package. This is very important. There's a 7-character typical hash for a particular installation of a package in Spack. So you can say Spack load a particular package, or it can say Spack load with a slash and give this hash. And so I'll try and load, say, a package deliberately that has the same version. So this will create an ambiguity. Spack will be confused. It will say, make up your mind, which one do you want to load? So I can say Spack load CMake at 3.18.4. Okay. When I know that there are 2 different packages, and it says there are 2 packages that match this. If you wanted to see exactly how they were built, you can say Spack find -dl with a -v flag for CMake. V is for verbose, so dependency listing, as well as show me how it was built. And you can see these are all the options with the patches and how it was built with the dependency. Now, if I have a particular version of Spack that I want to load, a specific version of the package, say this one, then I can say, or say this one, 13.8, and I can say Spack load with a slash over here, and then give that. This is similar to module load, and Spack in fact creates modules. So if you wanted to just stick with module avail and module load commands, that's just as well. But after doing this, I will have CMake in my path, which will be the 3.18. And if you see the directory where it is installed, it says it's installed in the directory for the compiler GCC 731, with which it was built. And here is the full hash of the CMake. But if you just see the first 7 characters, they match what I did over here with the module load. And so it's put the CMake from the bin directory from the Spack over here in this way. So there are other commands that you may find useful. One is a Spack location -i, and then you can give the same hash like this, and it will show you the location of this. Now you see it's not showing you the bin CMake, but the top level directory where it is provided. I could have said Spack location -i and then said CMake at 3.19.5, where there is no ambiguity. There's only one package like that. And then it would show me the location of the CMake 319.5 where it is installed. This is the directory. There are many packages in this directory. If you said ls, and you'll see all of these packages with their respective hash, so that you can have multiple versions of the same package built with different configurations. Okay, if I wanted to look at the program database toolkit package, I can say Spack location -I PDT, and I have PDT over here. I can look at Spack compiler list, and I can see different compilers. If I'm on a new system and Spack is installed, and I want to start using a particular compiler, I can just say Spack compiler find, and it will then find the compiler. If I load a compiler module and I say Spack compiler find, it will say, hey, I found a new compiler. I'm adding it to the .spack compilers.linux compilers.yaml file where I list all the compilers. If you are on a system where you say Spack external find, it will look for external packages like M4 or AutoConf or CMake in the installation on the system, and then it will just put it in the packages.yaml file so that it can be reused. So these are some useful commands that you can look at. And now I will I'll just wait for a question. Do you have any questions? Are you able to try these Spack commands, Spack load or Spack location? So the next step I'll take is taking the leap to a real ECP application. Let me go and use Spack to install an application that typically takes hours to build. But I will use the build cache. Build cache has binaries of various packages. So instead of building from the source code, which Spack, by the way, can do, it will download the binary and it will just install the binary for you. The package that I'm trying to use is the Exawind package called Nalu Wind. In fact, I have a quick set of slides on Nalu Wind that I can show over here. So this is a project from NREL, National Renewable Energies Laboratory. And these slides come from John Rood and Mike Sprague. And the Exawind project helps us understand and predict the impact of wakes on downstream turbines so that you can have a turbine farm like this, and you can see the evolution of wakes and formation of wakes in a highly complex dynamic environment. There are various packages. There's Nalu Wind, there's OpenFast, there's AMR Wind for adaptive mesh refinement. There is the paper. And there are solvers. There's the Tioga overset mesh coupling solver. There's the geometry resolving unstructured mesh Nalu Wind. And then there's the background structured mesh AMR Wind model. And you can see that there's near body and solvers like the Nalu Wind. And then there's the off body where the mesh can be coarser instead of this fine mesh, which is AMR Wind. And these two codes are coupled together using MPI communicators. Here is the complexity of offshore modeling, where you can see that you have wind farms that may be even floating in the water, and you can see the turbine going up and down, and then we have to solve for the equations, the hydrodynamics. And we have AMR Wind two-phase solver. Here is the Nalu Wind which is near body, and then the AMR wind, which is off body solver, and these two codes working together. And here is a simulation of the AMR wind and Nalu wind coupling, and the CFD simulation of the turbine. And you can see the complexity of building a package like the Nalu wind, where you have all of these packages and you're building them using Spack. And they have found that on systems like Summit, this whole thing can take over 4 hours, and even 2 hours to build on a 32-core Haswell machine. It internally uses Trilinos and Cocos. And we used E4S to speed up the installation. And what I'm going to try and do here is show you how to wipe out this Nalu wind and install it from the binary cache. And you will all do this, and then we'll run the Nalu wind on the test case. So here is my, so if I say Spack find Nalu dash wind, then it shows me where it is installed. Okay, I can say Spack uninstall Nalu wind. I'm uninstalling this package because I want to build it again and install it using the build cache. So it says yes, just say yes, and it will say it uninstalled this. I can double check that it's uninstalled by doing a find again, and it should say I don't have Nalu wind here. Okay, so now I can go to my home directory, and then I can go to this CD to the Nalu wind demo directory. Now, here is a spack.yaml file that describes the recipe for installing Nalu wind. And it shows you all the dependencies, it shows you which mpage to use. And it says, these are the compilers. And I want to use Nalu wind and enable certain variants. These are the variants, like I want to use FFTW and Hyper and OpenFast while building it. And then I want to use a build type of release with debug information. So these options you can enable. If I say Spack edit Nalu wind, I can see the original recipe for this package. And here is the recipe written in Python, which describes various options, the various variants that I may be able to enable. Like I have enabled OpenFast or Tioga or Hyper or FFTW. So it says compile with this. It depends on MPI, it depends on Trilinos like this, and other options that you can see in this recipe. So I have now a spack.yaml file over here. And I'll say spack-e. So I'm saying, please use the environment that is in the current directory. So in the current directory, it will find the spack.yaml file and then install it. So it finds all these other packages, and now it's fetching this file from the build cache, the build cache that exists on this directory. And then you can see that it's installing it from the build cache right before us. So this complex HPC application will be installed in seconds using that Spack build cache. It has GPG keys, it verifies the binary, and then it puts the application over here. And then I can run it. I'll run it by just running the .demo.sh. So I can say cat demo.sh, where it's going to the directory where the test files are. And then I say run with tau. This is running it with tau performance system. Sorry, I should say demo.sh. That goes and runs it with tau. And then this takes a couple of minutes. It deletes all the previous files, and it has just the YAML file, and it runs it with the Nalu wind. So while this is running it, let me just check if there are any other questions on this or what we just did. I uninstalled the Nalu wind application, then I went here, I said demo.sh, and then I can see exactly what it's doing. If I look at the run.sh and run tau.sh. By default, I'll just run the Nalu X application after loading it with Spack. And then I coalesce all the output files from 8 of those processors to make a single output.e file. And if I want to run it with tau, the tau profiling tool, I just need to change the MPI run and say tau exec -ebs. And there are certain other tau flags that I have listed here. And then run the Nalu X. So event-based sampling. The application is being interrupted periodically, and we are measuring the time spent in various code regions using that Nalu X. And this is the input file, edge hybrid fluids.yaml. So if I look at the top, you can see 100% 8 of these CPUs are busy running this ECP application. Now it takes a couple of minutes to run this. It has the whole Trilinos set of libraries and COCOs that it uses. But I wanted to give you a feel for running a real CFD code, which takes some time and then generates performance data so that we can visualize the output and so on. Were you all able to do this Spack uninstall, then CD to this directory, build it, and then run the demo.sh? Running okay for you, Benjamin? Okay, great. So it will take some time to do this, but I'll just pause and see if there are any other questions while this is running. At the end of this, we will have the output.e file that will be generated. Now, it's not generated in this directory. Note that I did the demo.sh, it did the CD to that other directory. So to look at the output.sh, I must CD back to that directory. And then here is the output.e file. This is the output file. Now, how do I view this output? If I want to see what the problem was, I have, this is the problem that we are trying to solve. Is the PDF of our slides. And at the very end, you'll see that description of the problem. And this is the test case. Now, if I say which paraview, I already have paraview in my path. Paraview is the visualizer. And this is the first big graphics program that I'm launching, besides the visit that I used earlier. And I'll say output.e. So now I'm visualizing the output.e file where I see the fluid flow over a plate. And I will be able to visualize this. demo.sh is still running. Of course, it will take some time. But after it ends, remember you need to cd to this demo directory like that. And then open a terminal window, go to paraview, and then say paraview output.e. So here is the output.e. It's loaded in paraview. But I cannot see the three things that it calculated until I check this box. The three things are pressure, turbulent viscosity, and velocity. I'm going to check these boxes like this, one after the other. And then I'll click the apply button. Now I can see this geometry. There's a fluid that is injected over here, and then it flows through this. And this is the surface. I can move this. I can look at, say, what is the velocity by clicking the velocity over here. And instead of the surface, I can say, show me the surface with edges. So here is the surface with edges. Let me use the middle mouse button to go deeper like this. Zoom in. You can see the geometry over here and then move it in the 3D view of paraview. I can click the play button over here and it will play the output of this program execution. So the velocity, I can look at the turbulent viscosity. So when you open up this, go to turbulent viscosity, look at surface with edges, and click the play button, and you'll see some movement over here. But I want to visualize the pressure. So I'll go to pressure, and here's the pressure, and press the play button and see how the pressure evolves over the execution of this code. Here is the point Gaussian, which shows me the full geometry of this particular test case and what it did. Now, this is, mind you, a very simple simulation. It took about 2-3 minutes on the application, but I hope you are able to then look at this 3D model, rotate it all through your web browser using DCV. And all I did is I checked these boxes, 3 of these boxes over here, clicked on apply, and then picked the turbulent viscosity, and then click the play, or pick the surface with edges, and then look at the small changes. So it's just enough to know that this ran properly. The fluid was injected over here, and then I can look at the pressure on the surface during the various execution phases. So this is a computational fluid dynamics code. Everything is running within the AWS environment over here. But it also created a profile file, which is tau profile.xml. And I can view it as tau profile.xml like this. And I did not need to change the binary in any way. I was able to just take the application and run it on 8 CPUs. And you can see these are the 8 MPI ranks where the performance data is shown. If I click here, it shows me where it's spending its time. And I can right click here and say, show me the thread statistics table, the third option on any node. And it shows me that the application took so much time. So here it took 50 seconds in a code region called Belos pseudo block GMRes solution manager with the total solve time. And it shows me a little key over here. I can see the names of the Cocos functions that it uses, because Cocos and tau can interoperate, and it shows you exactly where the time gets partitioned. And when a user writes out the parallel for routine, it can see exactly where that is. So you can drill down into the code and say, well, 33 seconds were spent here, 20 seconds were spent in Chebyshev apply function in LF Pack2, and these are the Cocos parallel fors. And you can see over here various functions. You can sort it by the time spent in it. Here is a parallel for which says Sierra Nalu, and within this I can, let me just expand this window. I can expand this, go here, look at the Sierra Nalu sum, where it's spending this 1.4 seconds. It uses sampling over here. I can right click here, say, show me which is this function. And this is a big templated code where it's spending close to a second on node 5 along this templated instantiation in the Cocos parallel for. It also has a line number over here in the T-Petra system. You know, if I look at the Sierra Nalu, it says, show me the source code. It will show me this line of code where it was spending that time. So I can see a line by line level profile, which shows me the sum into row vec3 function in the Cocos function, templated function, and that line of code where it was spending that time. I can also see the 3D visualization of this and see what each of those 8 ranks were doing. So here is the bar plot, and I can look at the bar plot where I see 8 MPI ranks, all the code regions, and what each region took in terms of the time in seconds. Here is the mesh, so I can see the 3D view. So I can visualize the data output using ParaView. I can look at the performance using ParaProf from Tau and drill down to the statement where it was spending its time, or see exactly how much time each rank took on each operation using the Cocos profiling interface. So let me just pause over here and see if there are any questions. I know we are at 11:34. We were supposed to have this at until 11:30. But are you able to look at this? Can somebody just confirm that this demo.sh ran completely and produced the output.e file? Yes. And if you say cd to the directory where it is installed, you should be able to generate the Tau and ParaView output and launch Tau over there. Okay.
And Samir, I think you said that you'd go, the schedule says 11:45, I think. So
11:45. Okay, so this is good. Let me just repeat what I did here. I did a ParaView output.e and launched it. And here, when it comes up, it doesn't show me anything, but I need to click on this pressure, turbulent viscosity, and velocity, and then click this apply, this green apply button. And that's when this geometry is available to me, and I can see, I can look at this geometry with surface with edges like this. And I can see, instead of VTK block, I can say turbulent viscosity. And this is the turbulent viscosity parameter that is saved. And then I can play it or go to pressure and then click the play button. And you should be able to see the change in pressure on this plate when the fluid is injected over here. There are many other cases of CFD examples that are there in the directory just above the demo directory. You can look at those at your own pace. But the idea is that they invariably produce some results from the simulation that you can visualize in the output file, and then see that output like this. Is this clear? Is there any, are there any questions? Were you able to get the 3D view? And Zach, were you able to visualize the output in ParaView?
Yes, I was able
Okay.
to visualize the output in ParaView, and if you want to adjust the color map scaling, there's the button, the two buttons left of that pressure drop-down menu will adjust the color map to the range of the animation.
Okay, these two, the color map setting.
Well, the couple more buttons in, but at any rate, I think it doesn't really matter. We are able to see.
Okay, and it produced the tau profile.xml file. You say paraprof tau profile.xml. You can see the global view with the 3D visualizer and see what each rank was doing in different code regions. You can see the bar plot. You can even move the function and the thread slider like this to see exactly which, like this nalu met precondition function took so much time, the scatter plot, and so on. Just a second. Sorry. I hope this works for others as well. And you can right click here and see the thread statistics table, see where the time is being spent in this 50 seconds spent in this solver, drill down to the solver and see how many seconds, 33, 20, and the exact exclusive and inclusive time at the source level, and see where it's spending how much time. The last part that I wanted to cover was that what if I want to create a Nalu wind container myself? And to do that, you can cd to the exawind containers directory. And here I have a spack.yaml file, which describes which variants I want to use for various packages. And I have 3 specs. I want to install tau, I want to install AMR wind, and I want to install Nalu wind with these variants. Okay. And I have over here a container recipe for building a Docker image using the Docker file. So here is the Docker file, and I'm using the run command. As you see, I'm using the daisy chained and options like this. And I'm using the build cache, the cache.e4s.io to create this. So I can just say build docker image.sh. And then it copies it from there, it builds it, and then it runs it. Now I have Docker images, and then this exawind container is created. I'm going to say Docker. I have used Docker save and then given it a exawind.tar with the local host ECP E4S exawind.latest. And then I can save this Docker image in a tar file. Just snapshot the whole image. And I have already done this. I have a Docker exawind.tar file. And then finally, I can say build Singularity container image like this using the definition file over here called exawind.def. And it just picks up from the Docker archive and then just adds a prompt called exawind Singularity container and creates a Singularity image, which will be called exawind.singularity image format or .sif. So I'll say build singularity image.sh, and then it asks me for the password, and then I'll give the tutorial password, and now it will build the singularity image. And you could create a very custom container, which will be a fraction of the size of the full E4S container by just cherry picking what you need and nothing else. And then create such a optimized container for your application aided by the build cache. It's picking up all the binaries from the build cache. It will just put them in the exawind containers. And then finally, I will have, let me just increase the size of this. It will create an exawind.sif file, which will be a small file from this. So what did we just cover? Besides learning about how to create a simple Docker or a Singularity container, we learned about Spack. We learned about the use of build caches. We substituted MPI. We also looked at removing the Naluwind application and installing it using the build cache. Then we went and we ran the bare metal installed version of Naluwind with the test case, and then launched the ParaView tool after running it for about 2 to 3 minutes, and looked at the output.e file. We also looked at the paraprof tool for looking at the performance of the code with no changes to the binary, where we could go deep into different code regions of Cocos and the statement level and see where the code was spending its time. And then finally, using the Docker file, we created a Docker container of the exawind application. And you can use the Docker run command with the image that we have created, or you can create a Singularity image and then say Singularity run, go to that directory and rerun that with the run.sh command and get the output file. And we have a local copy of the build cache. You can create your own build cache. You can create your own mirrors and host these binaries that you sign yourself. But the message I want to give here is that Spack is a versatile package manager that supports the binary build caches. You can create your own or use the one from E4S, which has over 50,000 binaries for different architectures, compilers, and we are constantly updating that build cache so that if you are trying to install a package that has a complex set of dependencies, you could just point to the E4S build cache and then get the binaries over there. So any questions with what we just covered? Should we? We'll continue with this tomorrow as well. And we'll look at other options. We have other containers that are in this image. We even have a container with OpenFOAM CFD package. And we'll look at that and how to run that. But I'll cover some more about using the binary image. And you can see that this is building the Singularity image on the AWS. So this will be an optimized container with just 3 packages and not all the packages, by using our build cache and the image that we created. So were you able to run all of these cases? The Singularity, sorry, the Naluwind example? Were you able to launch ParaView? Did the 3D graphics work okay with web-based remote desktop? ParaView worked for you? Good. So we started very simple. Uday, it worked for you? Very good. And it's building the Singularity Docker container for you, Zach. So starting from the very basics of how to create a Docker container or a Singularity container, we've gone to the point today in just a couple of hours to seeing how we can target a full ECP application and run it on AWS, and how to use optimized containers, how to create your own build caches, how to use the build cache to create your own containers. Is Mike here? Did you want to?
Yeah, Samir, I don't know that Mike was coming back for the
Okay.
today. He'll
So
be on tomorrow morning. So
he'll be here tomorrow. Okay, we'll have a session tomorrow. And Dimitri, that's a very good question. You said, how do I run multi-node jobs with containers? Well, you use the E4S CL launch command, and the MPI run arguments that you gave over there were just the arguments that you would use in a multi-node job, whether it is launched with B sub or whether it is with S run or MPI run. And here, for example, if I had two nodes and I was looking at the Zoltan and I say run E4S CL.sh, so all that would change would be this MPI run with the -- host option that specifies the host names, and then you would specify, say, -np64 and run it on two nodes or multiple nodes with the host file that you get from, or however you run your MPI job on a multi-node configuration. You just use the E4S CL launch before that, and then you are able to run the MPI job with the Intel MPI. So it will use the communication infrastructure more efficiently. Does that answer your question, Dimitri?
I had a follow-up question about E4S.
Sure, please. Go ahead.
CL. I noticed you did a lot of stuff. You set up the Intel MPI and that kind of thing. What was it in the environment that E4S CL knew to look at to make the substitutions? Is it your LD library path or your path?
Yes, it is a substitution of the LD library path and also mounting the external environment in the execution of the actual binary, because we are running this in the container, but we have to take all the libraries from the inside the container and then mount the Intel MPI libraries. And it, if you remember, it said it found like 10 different libraries that it had to process and then get. In some cases, finding the libraries can be very difficult. I have seen cases where you had to actually run the code once, and then it looked at the Mellanox libraries that were encoded in some Mellanox file in the etc directory, but you didn't know the name of that library until you read the file that had the name of that library, and you had to DL open that library. So for a user, that can be fairly complicated to figure out exactly how to get that full manifest of what needs to be loaded in the container before you can run it. You see my point?
Yeah.
So that's what the E4S CL tries to do for you.
Yeah. I forget what the magic was behind the scenes, that it was keying off. If I have my environment set so that I can successfully run an Intel MPI program, and then I use E4S CL to launch, it knows I'm intended to use Intel MPI.
Yes, it does.
Yeah, okay.
Directly, exactly. It's just a way to simplify your launch command so that you don't have to worry about doing this. Now, if you had a compatible GCC MPI with the same versions and you were able to just LD preload it yourself, there's a good chance that it will also work without the use of E4SCL. But then you have to figure out all those things yourself, and then supply the right LD library path and mount the directories yourself, which is what this tool tries to help with. So you just give it 3 parameters: the singularity, the name of the container, and what you need to source, and then the init does the magic and figures out all the libraries.
Right.
Any other questions?
This might be too involved of a question, so feel free to punt on it, Samir. But I was just wondering, sort of putting all these pieces together, I think the E4S ecosystem is available, or at least designed to be relatively easily used on DOE supercomputing systems. And I'm wondering if there's sort of a straightforward list of steps or components that you could follow, or components that you could grab to leverage some of this on a different computing system.
So our binary build caches are based on the operating system and compilers. So it could be on any system, not just DOE. They are not DOE specific, and you can launch the containers, the full featured containers on any HPC system with just Singularity that's typically installed. So on most of the, say, DoD systems, you might find that Singularity is pre-installed over there. So as long as you don't have to build your container, if you are just trying to just run it, you can just download this one big image, which has all of these different GPU components and packages, and just install it and do a Singularity run on the container, and you get an environment that is productive and useful. Instead of trying to install a Fortran compiler and MPI yourself in such an image, you already have everything pre-installed for you.
And can you install or bring over E4SCL to perform the MPI swap on a Singularity container?
Yes, you can easily install
Okay.
E4SCL. It's there on the GitHub page. You just do a git clone. It's all under MIT license. You can easily install that and just point it to the MPI and the container, and give it the name of the container and initialize it, and it will do the substitution.
Perfect. Thank you so much. Sounds too easy. I'll have to do some experimentation.
Sure. And we have these images on AWS where everything is pre-installed, so that even the base image on AWS has quite a few tools that may be useful for a productive environment. I know a lot of industry folks prefer to use a cloud-based environment, and so that that can be a useful feature. I hope you found this tutorial useful. We'll continue on tomorrow.